All right, for my next transient problem, I chose to do 5.54. The problem is, as part of the treatment process, cylindrical 304 stainless steel rods of 100 millimeter diameter are cooled from an initial temperature of 500 C by suspending them in an oil bath at 30 degrees C. If a convection coefficient of 500 watts per meter squared Kelvin is maintained by circulation of the oil, how long does it take for the center line of each rod or of a rod to reach a temperature of 50 degrees C, at which point it is withdrawn from the bath? If 10 rods of length equal L equal to 1 meter are processed per hour, what does the nominal rate at which energy must be extracted from the bath, or the cooling load? So just recording some of the givens that we should take note of: temperatures, properties of the material and the rods themselves. We know what we need to find, the time until center is 50 degrees, and how much energy needs to be taken from the bath. And then for our assumptions, we have a uniform initial temperature. We're going to neglect radiation. We have uniform radial conduction, uniform convection, and constant properties. So starting off, as we usually do, we're going to find the BO number. As this is a cylinder, our characteristic length will be radius over 2 or the diameter over 4. So there it is. And then calculating that out, we have 0.6578, which is less than or greater than 0.1, so it's going to be first term. So using that number, we're going to go ahead and go into the book and find some numbers for lambda and C1. Now, as it came out, because that was for testing whether it would be first term or lumped. Now we need to go ahead and calculate again the BO number for first term in particular, and we get 1.316. Then we can go to the book and linear interpolate between 1 and 2 to find our lambda and C1 values of 1.364 and 1.248. Knowing that, we can go ahead and come down here and using the similar dimensionless temperature parameter as we did in problem 5.47, we can solve using this relation here of the parameter equal to this equation here with Fourier's number in it, also equal to this difference between temperatures. So we all know all our temperatures, so we're going to go ahead and solve that ratio out for 0.04255. And then using that number, as well as knowing C1 and lambda 1, we're going to go ahead and calculate for Fourier's number. So then, using those, calculate for Fourier's numbers, and then directly back out time from the Fourier number equation, which I kind of did in one step here. So I got time is equal to about 1,031 seconds, or 17.2 minutes. So now that we have our time, we can go up here and use our Q max equation, which consists of density, specific heat, volume, temperature difference, and then an equation here that includes a Bessel function. So just knowing we need to get that, let's go to the book. I noted it as page 957. So they give a range of BO numbers, and then you can go ahead and interpolate for the accurate Bessel function equivalent. So staying in the middle here with 1.36 like we calculated earlier, or 1.316, pardon, I went ahead and solved for a Bessel function number of 0.5348. So going from there, we can go ahead and plug, as we know, practically everything else from either the givens above or just from properties of 304 steel given in the book. We can plug everything in here and solve for Q, which we get in joules. So now that's the max energy load from one rod irrespective of time. So now we need to go ahead and add time and the amount of rods into the equation. So we have this Q bar is equal to N times Q over the time final. So plugging those things in, we go ahead and we get 1.49 e to the 5 watts. And that's that.